Far beneath the surface of the western Pacific, beyond shipping lanes and storm systems, the ocean floor bends downward into a place sunlight has never reached. Depth here is not a gentle slope, but a sudden surrender, a vertical descent where Earth folds into itself. Geologists gave this place a name, Galathea Deep. The ocean covers more than 70% of Earth's surface, yet less than a quarter of its seafloor has been mapped in high resolution. Along the Philippine Trench, one tectonic plate slides beneath another, forming a narrow scar that drops almost as deep as the Mariana Trench, but receives only a fraction of its attention. At 10,500 meters, pressure exceeds 1,000 times what we feel at the surface. It rises with every 10 meters of descent, pressing inward on steel spheres designed to survive forces that can crush solid hulls in seconds. A hairline crack is not a flaw, but a countdown. Light fades within the first few hundred meters, and far below, temperatures hover just above freezing. The trench walls are steep and unsettled, shaped by subduction and frequent earthquakes. Sediment can give way without warning, falling in underwater avalanches along slopes that are anything but still. Communication slows to faint acoustic pulses. Rescue from 10 kilometers down is nearly non-existent. Only a handful of missions have reached such depths, and equipment failure becomes more likely the deeper we attempt to go. Yet life has been recovered from similar pressures, organisms adapting to conditions once believed impossible. But why does this vast trench remain so rarely visited compared to its deeper neighbor? What happens to metal and machinery when 1,000 atmospheres press from every direction? How does life persist where light never reaches and the cold never lifts? And what waits along a tectonic boundary that is always in motion beneath the sea? Tonight, we begin descending toward a frontier shaped by pressure, darkness, and shifting Earth. But before we begin, if you enjoy these journeys, gentle, soothing, and filled with wonder, I would be grateful if you gave this one a soft like and perhaps tapped subscribe. It helps other curious dreamers find their way to this peaceful little corner of the internet. And if you would be so kind, let me know in the comments, where are you listening from tonight, and what time is it where you are? It is always a joy to see how far across the world this little sleepy corner of science travels. So now take a deep breath, let your shoulders loosen, and together, let us drift slowly toward the deepest point of the Philippine Trench. Far from shipping lanes and crowded coastlines, the seafloor east of the Philippines bends downward into a long and narrow scar known as the Philippine Trench. Along its deepest curve lies a point called Galathea Deep, a depression carved where one immense slab of earth slowly sinks beneath another. It does not announce itself with storms or surface turbulence. From above, the ocean reveals nothing of the vertical distance hidden below. Measurements taken across decades have traced this descent with increasing precision. Early expeditions relied on weighted lines lowered patiently into the dark, their readings shaped by currents and uncertainty. Later, echo-sounding pulses traveled downward as brief bursts of sound, striking the bottom and returning as faint signals. Modern multibeam sonar has refined those estimates, mapping the trench floor in overlapping swaths. The deepest confirmed readings place Galathea Deep at more than 10,500 meters beneath sea level, a depth verified through repeated surveys and cross-checked by different research teams. Even now, slight variations appear in published figures, small shifts caused by equipment sensitivity, seafloor movement, and the complex geometry of the trench walls. In global rankings, it stands just behind Challenger Deep in the Mariana Trench. The difference in depth amounts to only a few hundred meters, yet that small margin has shaped public imagination. Challenger Deep has become shorthand for the deepest place on Earth, a superlative that attracts funding, headlines, and national ambition. Galathea Deep, nearly as profound, rests in comparative quiet. Fewer missions descend here, and fewer documentaries linger over its coordinates. Attention tends to follow records, and second place often fades into the background of scientific storytelling. Beneath this hierarchy of names lies a simple geological process. The Philippine Trench marks a boundary where the Philippine Sea Plate presses against the Eurasian Plate. Over millions of years, the denser plate has bent and slipped downward, sliding into the mantle in a motion measured in centimeters per year. This gradual sinking is called subduction. As one plate descends, it drags the seafloor into a steep trough. Rock fractures, sediments accumulate, and the trench deepens through time. The motion is slow enough to escape human senses, yet powerful enough to reshape oceans and continents across ages. Galathea Deep is therefore not an isolated pit, but a visible expression of planetary recycling. Crust formed elsewhere is carried downward here, beginning a journey back into Earth's interior. The numbers that describe its depth are more than measurements. They are markers of an ongoing collision, written in stone and water, a foundation set in motion long before any vessel traced its outline. Pressure at depth is not a sudden event, but a steady arithmetic written in water. For every 10 meters of descent, another atmosphere is added to the weight already pressing inward. At the surface, the body rests beneath a single layer of air. A few meters below, that load quietly doubles. 1,000 meters down, it has multiplied 100 times. At 10,500 meters, the surrounding force exceeds 1,000 atmospheres, more than 15,000 pounds pressing against every square inch. This weight does not announce itself with sound or motion. It is constant and absolute, flowing equally from all directions. Water, unlike air, cannot be compressed easily, so it transfers force with relentless efficiency. Any pocket of gas carried downward begins to shrink as the descent continues. Lungs, if unprotected, would collapse. Hollow spaces inside equipment tighten and deform. Even tiny bubbles trapped within materials are squeezed into invisibility. Living cells endure because they contain almost no empty space. Their interiors are filled with fluid and dissolved molecules, which resist compression more gracefully than air. Proteins and membranes flex at microscopic scales, maintaining structure without relying on cavities. Machines, however, are often built with gaps, seams, and compartments. In the deep, these become vulnerabilities. Submersibles designed for HODL missions are shaped as spheres for this reason. A sphere distributes external pressure evenly across its surface, leaving no corners where force can concentrate. The walls are forged from thick titanium or specialized steel, sometimes several inches dense, forming a pressure boundary between crew and ocean. Inside that shell, life support systems regulate air and temperature, creating a fragile island of surface conditions. The difference between stability and disaster can be measured in millimeters. A hairline crack in a pressure hull may appear insignificant under ordinary circumstances. At extreme depth, it becomes a pathway for catastrophic failure. Water seeks equilibrium with unstoppable determination. If the integrity of the sphere is compromised, the surrounding force rushes inward faster than human reaction time. The implosion would occur in milliseconds, collapsing the structure before thought could register the change. Engineers calculate tolerances with meticulous care, testing materials under simulated loads that mimic the trench. Bolts, seals, and viewports are examined repeatedly because each component shares responsibility for resisting the immense external weight. There is no gradual warning when limits are crossed. Pressure does not build toward drama, it simply remains patient and unyielding. At such depths, survival depends on understanding this invisible arithmetic. Every additional meter compounds the burden. Every descent is an agreement with physics, acknowledging that water at 10,500 meters is not merely deeper, but fundamentally different in the force it exerts. Emergency plans in the deep ocean are written with an unusual honesty. They begin by acknowledging distance, not only horizontal miles from shore, but vertical kilometers of water that separate a crew from open air. Once a submersible begins its descent toward the trench floor, it commits to a timeline that cannot be hurried. Ascent is not a simple reversal of descent. Ballast systems must function precisely, releasing weights or adjusting buoyancy in controlled stages. Rising too quickly can strain the structure and its occupants, while mechanical failure can leave a vehicle suspended far below the surface. Even under ideal conditions, returning from hadal depth requires hours. There is no rapid elevator to the sky, no immediate corridor back to daylight. Support vessels remain at the surface, often days from the nearest port. They track the submersible through acoustic signals that travel slowly through seawater, carrying short bursts of coded information. If communication weakens or stops, the ship can only wait, listening for faint replies. There are no nearby backup submarines idling at comparable depths, ready to intervene. Each mission typically deploys a single crewed vehicle, accompanied by remotely operated systems that cannot tow or retrieve a disabled craft from the deepest zones. Rescue technology has limits defined by pressure tolerance and cable length. Many established recovery submersibles are designed for continental shelf incidents, where depths are measured in hundreds rather than thousands of meters. Beyond certain thresholds, cables become too heavy, remotely operated vehicles lack sufficient structural strength, and lifting systems exceed their engineered capacities. At extreme trench depths, the equipment capable of reaching the site is often the same equipment already engaged in the mission. Time, in such circumstances, acquires a different texture. Life support within a submersible is finite, calculated carefully before launch. Oxygen supplies, carbon dioxide scrubbers, battery reserves, and thermal control systems are all balanced against expected mission duration. An unexpected delay narrows those margins. Surface crews can coordinate search patterns, adjust sonar sweeps, and prepare contingency plans. Yet, they cannot accelerate the physics of depth. For these reasons, trench expeditions are planned with deliberate caution and a degree of solitude. International cooperation exists in ocean science, but specialized hadal vehicles are rare and expensive. Transporting them across oceans requires months of preparation and considerable funding. As a result, most descents operate as self-contained efforts, relying on their own engineering redundancy and procedural discipline. In this environment, rescue is not assumed as an external guarantee. It is integrated into design philosophy from the beginning, embedded in thicker hulls, redundant systems, and rigorous testing. The ocean at such depths offers no convenient second chances, only the quiet demand that preparation account for isolation long before the first ballast weight is released. Beneath the calm surface currents, the crust is never entirely still. Far below the descending vehicle, rock presses against rock along a boundary that has been moving for millions of years. The trench marks the place where one tectonic plate slides beneath another, not smoothly, but with friction that builds slowly and releases without warning. As the denser oceanic plate bends downward into the mantle, it does not glide like silk. Its leading edge catches against the overriding plate, locking in place while deeper sections continue their gradual plunge. This mismatch in motion stores energy within the crust. Layers flex and strain, accumulating tension over decades or centuries. When the stress exceeds the strength of the rock, the boundary slips. The release travels outward as seismic waves, rippling through solid stone and into the water above. The region surrounding the trench records these adjustments regularly. Instruments placed on nearby islands and seabeds detect earthquakes ranging from subtle tremors to powerful jolts. Some originate deep within the descending slab, where minerals change structure under increasing temperature and pressure. Others occur closer to the surface, where the plates grind and momentarily break free. Each event reshapes the geometry of the boundary in small increments, altering stresses that remain hidden from view. During a descent, a submersible moves through water that appears undisturbed, yet the ground far below carries this restless history. A distant quake may register only as a faint vibration transmitted through layers of sediment and seawater. In many cases, crews might not perceive anything at all, while surface monitoring stations note the event hours later. The ocean dampens motion, absorbing and dispersing energy before it reaches a fragile sphere suspended kilometers above the fault. Still, the possibility of tremors is part of the environment. Seafloor observatories have shown that trench slopes can shift subtly after seismic events, adjusting their angles by fractions of a degree. Rock faces fracture, and fine particles loosen from steep walls. These changes do not transform the trench in an instant, yet they contribute to a landscape that evolves continuously. The descent path taken on one mission may not mirror precisely the terrain encountered on the next. In this setting, the seafloor cannot be described as geologically quiet. It is part of an active subduction system, a boundary where Earth's outer shell recycles itself. The same forces that build mountains and trigger distant tsunamis are present here, though often expressed in movements too gradual for human senses. Beneath the slow glide of a research vehicle, the plates continue their patient convergence, storing and releasing energy in cycles that long predate exploration and will continue long after any single expedition concludes. Along the inner flanks of the trench, the seafloor does not descend in a smooth curve but in steep terraces and fractured slopes. These walls rise sharply from the abyssal floor, layered with sediments that have drifted downward for thousands of years. Fine particles from distant rivers, microscopic shells from surface waters, and volcanic ash from faraway eruptions settle gradually into this narrow corridor, forming thick accumulations along the incline. Gravity holds these deposits in a delicate balance. Each new layer adds weight to those beneath it, compacting the sediment and increasing the stress along buried planes of weakness. In some areas, the material is loosely consolidated, more like damp powder than solid rock. In others, fragments of older crust are wedged between softer layers, creating uneven surfaces where friction varies from 1 meter to the next. The trench walls become a mosaic of stability and strain. A subtle disturbance can tip this balance. A distant seismic pulse, a slow shift in the underlying plate, or the incremental loading of new sediment may reduce friction along a slope just enough for movement to begin. When it does, the slide can accelerate rapidly. What starts as a gentle slumping of material may transform into a cascading flow, carrying mud, sand, and broken rock downslope in a dense underwater avalanche. Unlike landslides on land, these flows are cushioned by water, yet they can travel great distances along the trench floor. As sediment moves, it displaces the water around it, generating currents that spread outward in rolling clouds. Fine particles are lifted into suspension, turning clear water opaque. For a submersible or robotic vehicle operating nearby, visibility can vanish within moments. Cameras that once captured sharp contours of the seabed record only a swirling haze. Sonar signals, which rely on the reflection of sound waves, scatter unpredictably when passing through dense plumes of debris. These turbidity currents may continue for minutes or hours, depending on the volume of material involved. Instruments anchored to the seafloor have documented sudden spikes in sediment concentration, followed by gradual settling as gravity reasserts control. The trench floor, once sharply defined, can be reshaped subtly by each event, smoothing some features while burying others beneath fresh layers of silt. Such processes are not rare anomalies, but part of the trench's ongoing evolution. Steep geometry and continuous sediment supply ensure that slopes remain dynamic over geological time. For those descending through this environment, the landscape is not fixed scenery, but a terrain capable of rearranging itself without warning, guided by gravity and the quiet accumulation of material along its walls. Long before a vehicle reaches the trench floor, engineers begin anticipating the quiet ways it might fail. Extreme depth does not attack with a single dramatic force. It works patiently against every seal, every strand of wire, every junction where materials meet. The ocean presses inward without pause, testing the smallest imperfection. Seals that appear flawless at the surface must withstand thousands of meters of compression. Rubber O-rings and polymer gaskets are designed to flex, creating watertight barriers around hatches and cable entries. Under immense pressure, these materials deform further, sometimes creeping microscopically out of place. A seal that shifts by a fraction of a millimeter can allow seawater to infiltrate compartments meant to remain dry. Once inside, salt water begins its quiet corrosion, shorting circuits and degrading metal contacts. Wiring harnesses face similar strain. Insulation that protects copper strands from moisture is squeezed tightly against the conductor. Over time and repeated dives, this compression can lead to microfractures in the protective layers. Water molecules find pathways along these flaws, migrating inward through capillary action. Electrical resistance changes subtly at first, altering sensor readings or disrupting communication between onboard systems. In the deep, even small inconsistencies can cascade into larger malfunctions. Batteries present another constraint. Most deep-sea vehicles rely on high-capacity lithium-based power systems sealed within pressure-tolerant housings. At extreme depth and low temperature, chemical reactions inside these cells slow. Voltage output may decline more rapidly than expected, reducing operational time. Engineers compensate with conservative energy budgets, yet extended missions can approach the limits of stored power. Recharging is impossible until the vehicle returns to the surface, so every light, thruster adjustment, and data transmission must be weighed against finite reserves. Robotic vehicles, especially remotely operated and autonomous platforms, encounter failure rates that rise sharply in hadal zones. Thruster bearings endure continuous load as dense water resists movement. Manipulator arms operate in near-freezing conditions, their hydraulic fluids thickening slightly under pressure and cold. Sensors calibrated in laboratory conditions respond differently when exposed to crushing forces. Cameras must peer through thick viewports that can distort images as pressure shifts their curvature. Electronics themselves are not immune. While solid-state components lack moving parts, they are housed within pressure vessels that must remain perfectly sealed. Heat generated by processors has nowhere to dissipate easily in insulated housings, creating thermal gradients that stress circuits. Repeated pressure cycles during multiple dives, fatigue solder joints, and microscopic connections etched into circuit boards. For these reasons, every descent carries an awareness of fragility. Redundant systems are installed, backup computers mirror primary ones, and critical functions are duplicated wherever weight allows. Yet, complexity brings its own vulnerabilities. At 10,000 meters, technology operates at the edge of its design envelope, sustained by careful preparation and an understanding that the ocean will probe each component without rest. Before any light fades completely, sound has already begun to change. In the upper ocean, waves and engines and distant storms mingle into a layered murmur. Deeper down, that mixture thins. Water, under immense pressure, carries sound efficiently, yet the sources of noise grow scarce, leaving long stretches where only the faint hum of onboard systems remains. Acoustic waves travel faster in seawater than in air, shaped by temperature, salinity, and depth. In the hadal zone, cold and compression alter their pathways, bending signals along curved routes through the water column. A message sent from the surface does not move instantly to a submersible below. It passes as a sequence of coded pings, each one taking seconds to bridge the vertical distance. Replies follow the same slow exchange. Conversation becomes measured, deliberate, separated by quiet intervals where nothing is heard but the vessel's internal circulation. Within the pressure sphere, the crew inhabits a space scarcely larger than a small room. Walls curve closely around them, layered with thick metal that holds back the surrounding ocean. The interior is orderly and compact. Instruments glow softly, gauges display steady readings, and checklists rest within reach. Voices are kept calm and economical, not because silence is demanded, but because there is little room for excess sound. Every movement carries a subtle echo against the spherical hull. Hours pass in this contained environment. The descent unfolds gradually, marked by incremental updates from depth sensors and navigation systems. Outside, there is no wind, no visible horizon, no shifting sky to signal time. Inside, awareness narrows to the cadence of breathing, the faint vibration of life support fans, and the periodic exchange of acoustic messages with the ship far above. The delay between question and answer becomes part of the rhythm, a reminder of distance measured not in miles but in vertical water. Sound itself behaves with restraint. There are no crashing waves or rushing currents at these depths, only the subdued transmission of mechanical operations and occasional distant tremors carried through the crust. Even the submersible's thrusters, when engaged, produce a muted resonance that dissipates quickly into the dense surroundings. In this quiet, isolation is not defined by absence of technology, but by separation from immediate response. Communication exists, yet it is filtered through layers of ocean and time. The crew remains connected to the surface, though not in the effortless way of open air. The silence below is therefore not emptiness, but a spacious pause between signals, a calm interval where human presence persists within a small sphere, suspended in a vast and patient sea. Color begins to disappear long before the trench floor comes into reach. Reds fade first, absorbed within the upper layers of water, followed by oranges and yellows. By 1,000 meters, sunlight has been reduced to a memory of itself, a faint blue trace that soon dissolves entirely. Beyond that threshold, the ocean is no longer dim. It is fully dark, untouched by any natural glow from above. In this realm, vision depends entirely on what explorers bring with them. Submersibles carry arrays of high-intensity lamps mounted around viewports and cameras. When switched on, these beams carve tunnels through the blackness, illuminating narrow cones of suspended particles and the contours of the seafloor. Outside those cones, darkness remains absolute. The boundary between light and shadow is sharp, as if the world exists only where the lamps are pointed. Artificial light alters more than visibility. It introduces a sudden presence into an environment that has evolved in near total obscurity. Many deep-sea organisms possess highly sensitive photoreceptors, adapted to detect faint bioluminescent flashes rather than broad illumination. When bright beams sweep across the sediment, some creatures freeze, their movements paused, as if blending into stillness offers protection. Others retreat slowly into burrows or crevices, leaving only faint impressions in the soft substrate. Certain species respond differently. Amphipods and small fish may drift into the illuminated field, drawn by curiosity or by the possibility of disturbed prey. Their bodies often appear pale or translucent, lacking pigmentation that would be useful near the surface. Without sunlight, color serves little purpose. Form and function replace display, and many features are shaped by touch, pressure, and chemical cues rather than sight. For human observers, the persistence of darkness reshapes perception in subtle ways. Inside the submersible, illuminated instruments provide orientation, yet the view beyond the glass remains confined to what the lamps reveal. There is no horizon to anchor perspective, no gradual shift from day to night. Time becomes abstract, measured by mission clocks rather than by changes in light. The mind adapts by focusing on immediate details, on textures revealed within the beam, on movements at the edge of visibility. In such conditions, light is both tool and interruption. It allows discovery while reminding the crew that the surrounding ocean exists independently of their brief illumination. When the lamps are dimmed or turned away, the trench resumes its uninterrupted blackness as it has for millions of years. The absence of sunlight is not an event here, but a constant state, a backdrop against which every descent unfolds in a small, deliberate circle of borrowed glow. At first glance, the trench floor seems too extreme to support complex life, yet careful observation reveals movement against the sediment, small shapes navigating a landscape shaped by pressure and cold. Among the most persistent inhabitants are amphipods, pale crustaceans that drift and scuttle across the hadal plain. They are often no larger than a fingertip, though some species reach surprising sizes, their bodies curved like commas against the dark substrate. These amphipods endure conditions once assumed to be beyond the limits of animal survival. Their exoskeletons are not heavy armor but lightweight frameworks, flexible enough to tolerate immense compression. Inside, their tissues contain little empty space. Fluids fill the gaps where air might exist in surface organisms, reducing the risk of collapse. Chemical compounds, such as trimethylamine N oxide, accumulate within their cells, stabilizing proteins so they do not lose shape under pressure. In this way, biochemistry becomes structural support, maintaining function where physics would otherwise disrupt it. Snailfish have also been recorded at remarkable depths, their gelatinous bodies appearing almost translucent in the glow of submersible lights. Unlike the rigid bones of shallow water fish, their skeletons are lightly ossified, with cartilage playing a greater role in support. This reduced density allows their tissues to compress without fracturing. Large pectoral fins help them hover just above the sediment, conserving energy in a place where food is sparse and movement must be economical. Within their cells, adaptations unfold at microscopic scales. Proteins, which rely on precise folding to perform essential tasks, are reinforced by molecular adjustments that preserve their shape despite crushing forces. Cell membranes incorporate specialized lipids that remain fluid even at low temperature and high pressure, preventing brittleness. Enzymes that drive metabolism operate at slower rates, tuned to an environment where energy arrives unpredictably. These organisms do not resist the trench so much as harmonize with it. Their physiology reflects long evolutionary refinement, shaped by generations that survived incremental increases in depth. Genetic studies suggest that some lineages have migrated downward over time, adapting step by step rather than appearing suddenly in the deepest zone. Life here is neither abundant nor flamboyant, yet it persists with quiet determination. Each amphipod and snailfish represents a solution written in chemistry and form, demonstrating that biological systems can adjust to circumstances that seem incompatible with complexity. In the stillness of the hadal realm, these creatures move deliberately across the sediment, sustained by flexible molecules and patient metabolisms, inhabiting a world where survival depends on yielding gracefully to pressure rather than resisting it. Survival in the trench begins at a scale too small to see. Within each cell, structure replaces emptiness. Air-filled cavities, common in surface organisms for buoyancy or respiration, have no place here. Under immense compression, any trapped gas would shrink dramatically, distorting tissues and disrupting function. Hadal life avoids this vulnerability by building bodies that are almost entirely fluid and solid, leaving no hollow chambers to collapse. Cytoplasm, the dense solution inside cells, behaves differently from air. Water resists compression, and dissolved molecules move within it without creating voids. Organelles float in this medium, suspended in a matrix that transmits pressure evenly. Instead of fighting the surrounding force, cells allow it to pass through them uniformly, minimizing stress on any single point. In this way, the ocean's weight becomes a constant presence rather than a sudden threat. At the molecular level, special chemical structures reinforce stability. Proteins depend on precise folding to perform tasks such as transporting nutrients or catalyzing reactions. High pressure can alter these folds, changing their shape and impairing function. Deep-sea organisms accumulate small organic compounds known as piezolites, including trimethylamine N-oxide, that bind subtly to proteins and help maintain their three-dimensional arrangement. These molecules act like invisible braces, preserving flexibility while preventing collapse. Cell membranes, composed of lipid bilayers, must remain fluid enough to allow substances to pass in and out. Under crushing force and near freezing temperatures, ordinary membranes could become rigid. Hadal species adjust the composition of their lipids, incorporating unsaturated fatty acids that keep the membrane supple. This fluidity ensures that transport channels open and close properly, sustaining life processes in conditions that would immobilize less adapted cells. Metabolism in the trench proceeds at a measured pace. Food is limited, and energy conservation is essential. Many deep-dwelling organisms exhibit slower growth rates and extended lifespans compared to their shallow water relatives. Enzymatic reactions occur efficiently but without haste, balanced against the steady availability of nutrients drifting from above. By reducing metabolic demand, these creatures lower the risk of imbalance in an environment where recovery from stress may be difficult. Over generations, such adjustments accumulate into unique adaptations. Skeletal structures are minimized or reconfigured. Musculature is arranged to function under constant load, and sensory systems prioritize chemical and tactile cues over vision. Each trait reflects a compromise shaped by depth. Rather than resisting the crushing force outright, life here accommodates it, integrating pressure into its design. In the hadal realm, endurance is not achieved through rigidity, but through flexibility at every level, from molecules to whole bodies. The absence of air spaces, the presence of stabilizing compounds, and the rhythm of slow metabolism together form a quiet strategy for persistence beneath an ocean that never relaxes its grip. Food in the trench does not grow from sunlight or rise from warm currents. It arrives slowly from far above, descending through kilometers of water as a steady, delicate fall. Scientists call it marine snow, though it is neither cold nor crystalline. It is a mixture of organic fragments, microscopic shells, fecal pellets, and the remains of plankton that once floated near the surface. Each particle begins its journey in brighter waters, released from living bodies or formed through decay. Gravity draws it downward in a quiet migration that can take days or weeks. Along the way, much of it is consumed by midwater organisms, broken into smaller pieces or dissolved into nutrients. By the time it reaches hadal depths, only a fraction of the original material remains. What settles onto the trench floor is sparse, scattered, and unpredictable. Occasionally, larger events punctuate this slow drift. The body of a fish or squid may sink intact, becoming what researchers describe as a food fall. These rare arrivals create temporary abundance, attracting amphipods, snailfish, and other scavengers from the surrounding sediment. Activity intensifies briefly as animals gather, feeding efficiently before the resource is reduced to bone and residue. Such moments are infrequent, and the interval between them can be long. Scarcity shapes behavior in subtle ways. Many deep-dwelling species have evolved to conserve energy, moving deliberately rather than in bursts. Their digestive systems are capable of extracting nutrients from material that would seem insufficient elsewhere. Some amphipods possess enzymes that allow them to process tough, fibrous matter, even fragments of wood that have drifted down from distant forests. Microbes living within the sediment contribute by breaking down complex compounds, releasing simpler molecules that can be absorbed by larger organisms. In this environment, competition is balanced by low population density. The trench does not teem with life, and the limited food supply supports only a modest community. Reproduction may occur less frequently, and growth rates are measured over extended periods. Each organism occupies a niche defined by patience and efficiency, attuned to the rhythm of material settling from the upper ocean. The energy that sustains this ecosystem, therefore, originates elsewhere, carried downward in a continuous yet diminished cascade. Unlike surface ecosystems fueled by direct sunlight, the hadal realm depends on distant production and gradual transfer. The trench floor becomes the final resting place for countless particles that once drifted near the waves, and from these remnants, life constructs a quiet cycle of consumption and renewal, sustained by fragments of a world far above. Long after larger creatures drift out of view, life continues in forms too small to notice without magnification. Within the sediment and along fractured rock surfaces, microbial communities assemble in thin films and clustered colonies. They do not depend on falling fragments alone. Some draw energy from chemistry itself, sustaining metabolism through reactions that unfold quietly in the dark. Chemosynthesis begins with compounds released from the earth rather than from the sky. Where tectonic forces fracture the crust, minerals interact with seawater, producing substances such as hydrogen sulfide, methane, and reduced metals. Certain bacteria and archaea are equipped with enzymes that harness the energy stored in these molecules. Instead of capturing photons as plants do near the surface, they rearrange chemical bonds, using the released energy to convert carbon dioxide into organic matter. The process is less familiar than photosynthesis, yet it follows the same principle of building life from simple ingredients. In the trench, these reactions occur within sediments rich in buried material and along zones where fluids seep slowly upward. Microbes form layered mats that can coat grains of sand or line the walls of small fissures. Each cell contributes to a network of exchanges, passing metabolites to neighboring organisms. Some species oxidize sulfur compounds. Others reduce nitrates or iron, creating cycles that link one metabolic pathway to another. Together, they establish a compact ecosystem, structured not by light gradients but by chemical availability. These communities are remarkably diverse. Genetic analyses reveal lineages adapted specifically to high pressure, with enzymes that retain function under compression. Cell membranes contain lipids adjusted for both cold and force, maintaining permeability despite the surrounding weight of water. Growth rates are often slow, measured in days or weeks for a single division. Yet persistence over long periods allows populations to remain stable. Because they rely on geochemical energy sources, these microbes exist largely independent of sunlight. While organic debris from above contributes nutrients, the core of their metabolism can continue even in its absence. This independence expands the concept of habitable environments, suggesting that life does not require a direct connection to the surface world. Instead, it can emerge wherever suitable chemistry and liquid water coincide. In the still sediment of the trench, unseen communities conduct reactions that echo ancient stages of Earth's history. Long before oxygen filled the atmosphere, similar metabolisms may have sustained early life. Here, in perpetual darkness, those pathways remain active, linking rock and water through microscopic transformations that quietly uphold an ecosystem beyond the reach of the sun. Even here, where pressure dominates and light never arrives, traces of the surface world descend in unexpected forms. Among the drifting particles that settle onto the trench floor are fragments shaped not by geology or biology, but by human manufacture. Thin fibers, brittle shards, and translucent films come to rest within sediment that has accumulated over ages. Plastic, light enough to float when first discarded, does not always remain at the surface. Sunlight and waves break larger pieces into smaller fragments, increasing their density relative to seawater. Some become coated with microbial films and organic matter, a process known as biofouling, which adds weight and encourages sinking. Others are consumed by marine organisms and later released in fecal pellets that descend rapidly through the water column. In this way, material produced on land or in coastal cities can travel silently toward the deepest trenches. Surveys of Haddle sediments have revealed microplastics embedded within fine grains, interspersed among shell fragments and mineral particles. In some cases, researchers have recovered larger debris, including plastic bags and packaging, preserved by the cold and absence of ultraviolet light. The trench acts as a final repository, a place where sinking material accumulates because of its steep geometry and converging slopes. Gravity guides debris downward along submarine canyons and escarpments, funneling it into the deepest pockets. The presence of such material does not immediately transform the ecosystem, yet it introduces compounds that did not exist in Earth's oceans until recently. Certain plastics release additives and monomers as they slowly degrade, chemicals that can interact with microbial communities or be ingested by small invertebrates. Amphipods, sampled from Haddle depths, have been found to contain microscopic plastic particles within their digestive tracts, evidence that human influence extends beyond the reach of direct observation. Trench systems are particularly effective at trapping debris because they lie along tectonic boundaries that collect sediment from broad regions. Earthquakes and underwater landslides can mobilize material from continental margins, transporting it downslope in turbidity currents. Within these flows, natural and synthetic fragments mix indistinguishably, settling together once movement ceases. Over time, layers form that record both geological processes and the recent imprint of industrial society. The quiet of the Hadal realm, therefore, carries a subtle reminder of connection. Objects shaped in factories and handled briefly at the surface may endure for decades or centuries in these depths. The trench, shaped by planetary forces over millions of years, now also reflects patterns of modern consumption. Even in the most remote environment on Earth, the sediment holds evidence that the boundary between human activity and the deep ocean is more permeable than once imagined. Recognition often shapes exploration as much as depth itself. The deepest point in the ocean has become a symbol, drawing national pride, private sponsorship, and sustained research programs. Nearby trenches that approach similar depths exist in comparative obscurity, their names less familiar beyond scientific circles. This difference in visibility influences the flow of resources long before a vessel leaves port. Funding for Hadal expeditions is substantial under any circumstance. Specialized submersibles, reinforced support ships, sonar mapping systems, and months of preparation require millions of dollars. When attention concentrates on a single iconic location, proposals connected to that site may find stronger institutional backing. Laboratories can justify repeat missions, refine equipment through incremental testing, and maintain teams with experience specific to that environment. In contrast, trenches with fewer headlines often receive intermittent support, resulting in longer gaps between descents. Fewer missions mean fewer opportunities to refine logistics. Each expedition must assemble expertise, transport heavy equipment, and coordinate international permits. Without an established cadence of exploration, teams may need to rebuild operational knowledge each time. Lessons learned during one descent risk fading before the next is scheduled. Continuity becomes more difficult when voyages are separated by years rather than seasons. Geographic position adds another layer of complexity. The Philippine Trench lies east of the Philippine archipelago in a region shaped by active weather systems and seasonal typhoons. Research vessels must navigate long distances across open Pacific waters, carrying fuel, provisions, and spare parts for extended periods at sea. Port facilities capable of supporting deep-sea missions are limited, and transporting a full Hadal-capable submersible across oceans requires careful scheduling and significant expense. International waters and overlapping jurisdictions can also complicate planning. Securing research permissions involves collaboration with coastal nations and adherence to environmental regulations. These processes are essential but time-consuming, and they must be synchronized with vessel availability and funding cycles. Weather windows narrow the operational season further, compressing complex objectives into brief intervals of relative calm. In locations that host frequent expeditions, infrastructure gradually adapts. Data archives grow, seabed maps improve, and local knowledge accumulates. Where exploration is sparse, each mission begins with broader uncertainties. Sonar coverage may be incomplete, baseline biological surveys limited, and historical records scattered across institutions. Preparing for descent requires additional reconnaissance and contingency planning. Depth alone does not determine difficulty. The interplay of attention, resources, distance, and infrastructure shapes how often a trench is visited and how smoothly operations unfold. In the Western Pacific, where one trench commands global recognition, another of nearly comparable magnitude waits with fewer footprints on its floor. Its challenges rooted as much in logistics and funding as in the pressure of the sea itself. A descent to the Hadal Zone begins long before any ballast is released. Contracts are signed, shipyards prepare specialized vessels, engineers inspect pressure spheres, and research teams assemble across continents. Each of these steps carries a price, and together they shape an undertaking measured not only in depth, but in millions of dollars. The submersible itself represents years of design and fabrication. Pressure-resistant alloys, custom viewports, life support systems, and redundant electronics must meet standards far beyond conventional marine equipment. Testing requires hyperbaric chambers capable of simulating immense loads, facilities that are rare and costly to operate. Maintenance between dives demands careful disassembly and inspection, replacing seals, recalibrating sensors, and verifying structural integrity after each exposure to extreme conditions. Above the dive vehicle, a research vessel must remain on station. These ships are floating laboratories equipped with dynamic positioning systems that hold them steady over a target point despite currents and wind. Crews operate around the clock, managing cranes, winches, sonar arrays, and communication systems. Fuel consumption alone for a multi-week expedition can reach substantial sums, especially when voyages cross thousands of kilometers of open ocean. Scientific equipment adds another layer of expense. Multi-beam sonar for detailed mapping, remotely operated vehicles for preliminary surveys, sampling devices for sediment and biological specimens, and onboard analytical instruments all require investment. Specialists in geology, biology, engineering, and navigation must be transported and supported at sea. Salaries, insurance, and training accumulate quietly within the overall budget. Because of these costs, only a limited number of nations and well-funded private initiatives attempt repeated descents to the deepest trenches. Countries with established oceanographic institutions and access to advanced shipbuilding industries are better positioned to sustain such programs. Even then, missions are often collaborative, pooling resources across universities and agencies to distribute financial burden. The decision to allocate funding to a single descent reflects broader priorities. Governments weigh potential scientific discoveries against other demands on research budgets. Hadal exploration promises insights into plate tectonics, extreme biology, and Earth's history. Yet these benefits must compete with projects closer to shore or more directly tied to economic returns. A single successful dive may gather data that reshapes understanding of deep ocean processes, but the path to that moment requires sustained investment. Every hour at depth rests upon years of preparation and layers of logistical support. The trench may lie far from daily life, yet reaching it depends on complex networks of industry, science, and national commitment, converging briefly above a point in the ocean before dispersing again across the globe. Long before a submersible descends, the trench is traced by sound. Research vessels sweep back and forth across the ocean surface, sending pulses downward that spread like widening fans. These multi-beam sonar systems emit hundreds of acoustic signals at once, each one striking the seafloor and returning with subtle variations in timing. From these echoes, computers reconstruct depth and shape, transforming invisible terrain into digital contours. The principle is simple, yet the execution is intricate. Sound travels at different speeds depending on temperature, salinity, and pressure. Instruments continuously measure these variables, adjusting calculations so that each returning echo is placed accurately in three-dimensional space. As the ship advances, overlapping swaths of data accumulate, revealing ridges, slopes, and depressions along the trench axis. What emerges is not a photograph, but a textured relief map composed of millions of acoustic measurements. Even so, surface mapping has limits. The deeper the water, the wider each sonar beam spreads before reaching the bottom. At Haddle depths, this widening reduces resolution, smoothing small features into generalized shapes. Fine details, such as narrow fissures or steep micro-escarpments, may remain unresolved from above. To approach greater clarity, autonomous underwater vehicles are deployed. These robotic craft descend closer to the seafloor, navigating pre-programmed routes a few hundred meters above the sediment. Equipped with high-frequency sonar, cameras, and inertial navigation systems, they gather data at much finer scales. Without tethers, they move freely, storing information on board until recovery. Their proximity to the bottom sharpens images, revealing textures and structures that surface sonar cannot distinguish. Yet full mapping remains incomplete. The trench extends for hundreds of kilometers, and high-resolution surveys cover only portions at a time. Weather constraints, funding cycles, and the sheer duration required to methodically scan each section of slow progress. Autonomous vehicles operate within battery limits and must return periodically for recharge and data retrieval. Complex topography can also interfere with navigation, requiring cautious planning to avoid collision with steep walls. Sediment movement and seismic activity introduce another challenge. The landscape is not static. Underwater landslides and tectonic shifts alter slopes and redistribute material, meaning that maps represent moments rather than permanent records. Repeated surveys may show subtle changes, reminding researchers that the terrain evolves. Mapping the trench is therefore an ongoing process, a gradual refinement of outlines through layered expeditions. Each dataset adds depth and precision, yet the entirety remains only partially resolved. Sound sketches the contours, autonomous vehicles fill in detail, and between them lies a vast expanse, still waiting to be charted with patience and persistence. Numbers that describe the deepest parts of the ocean carry an air of precision, yet they are shaped by instruments that interpret echoes rather than touch the bottom directly. When a research vessel transmits a sonar pulse toward the trench floor, it measures the time required for that sound to travel down and return. Depth is then calculated from this interval, adjusted for the speed of sound in seawater. Small variations in that speed can influence the final figure. Sound does not move uniformly through the ocean. Temperature, salinity, and pressure alter its velocity in subtle ways. Even careful profiling of the water column cannot capture every fluctuation across a wide survey area. A difference of a few meters per second in sound speed may translate into several meters of depth variation when dealing with distances exceeding 10,000 meters. These adjustments remain within accepted scientific margins, yet they remind researchers that each measurement reflects a model as well as a direct reading. The geometry of sonar beams introduces additional uncertainty. From the surface, multi-beam systems emit fan-shaped arrays that widen as they descend. At extreme depths, the footprint of each beam on the seafloor expands, covering broader areas and blending fine features into averaged values. If the beam strikes a sloped surface rather than a flat one, the return signal may represent a midpoint along that incline rather than the deepest notch nearby. High-resolution surveys from autonomous vehicles can refine these contours, yet coverage is rarely uniform across an entire trench. Tidal forces also influence reported depths. The ocean surface rises and falls under the pull of the moon and sun, sometimes by more than a meter. Depth calculations are referenced to standardized sea levels, but instantaneous measurements taken during a survey must be corrected for tidal stage. Even slight discrepancies in timing can lead to small differences in published numbers. Seafloor dynamics contribute further variation. Subduction zones are not static. Gradual plate movement, sediment accumulation, and occasional seismic events can alter the shape of the trench floor. A depression measured one decade may deepen or fill slightly in the next. Such changes are often modest, yet over time they affect the precise value assigned to the deepest point. For these reasons, depth figures may shift by tens of meters between expeditions. The changes do not indicate error in a careless sense, but rather refinement as technology improves and conditions are better understood. Scientists report ranges and uncertainties alongside their measurements, acknowledging that the ocean's extremes resist absolute finality. In the Hadal realm, even a number as definitive as the deepest point carries with it a margin that reflects the complex path from sound pulse to calculated depth. Far below shifting weather and surface tides, the planet reshapes itself in silence. Oceanic trenches mark the boundaries where Earth's outer shell bends and folds, guiding vast plates into slow convergence. What appears from above as a narrow line on a map is, in geological terms, a gateway through which entire sections of crust begin a downward journey. Oceanic crust forms at mid-ocean ridges, where molten material rises and cools into new seafloor. Over millions of years, this crust drifts outward, carried by plate movement that operates at a pace measured in centimeters per year. As it ages, it cools and becomes denser. Eventually, when it meets a continental or younger oceanic plate, its weight favors descent. The trench outlines the place where this denser slab curves and slides into the mantle beneath. This process is known as subduction, and it serves as a recycling system for the planet's surface. Sediments, minerals, and even fragments of ancient ocean floor are carried downward, subjected to increasing temperature and pressure. Some material descends deep into the mantle, contributing to long-term circulation patterns within Earth's interior. Other portions melt partially, generating magma that can rise again through volcanic arcs on nearby landmasses. In this way, what sinks at a trench may one day emerge as new rock in a distant mountain chain. Plate movement driven by mantle convection creates a dynamic balance between creation and destruction. While ridges add new crust, trenches remove it. Without subduction, the ocean basins would widen indefinitely. Instead, Earth maintains a rough equilibrium, with the surface continually renewed. Trenches, therefore, play a role not only in shaping the seafloor, but in regulating the size and configuration of continents across geological time. These cycles unfold over spans far beyond human observation. The trench floor measured today will not remain unchanged through the ages. As plates continue to converge, the geometry of the boundary evolves, influencing seismic activity, volcanic patterns, and the distribution of land and sea. Even climate is linked indirectly to this slow choreography, since volcanic emissions and mountain building affect atmospheric composition and weathering processes. In the hadal depths, where the crust bends into the mantle, the planet's surface is not static but transitional. Rock that once lay beneath open water may eventually contribute to new terrain elsewhere. The trench becomes a hinge in Earth's architecture, a place where the outer shell folds inward and participates in cycles that have operated for billions of years. Through this continual recycling, the planet sustains a landscape that is never fixed, always in motion, guided by forces deep within its interior. When tectonic plates shift abruptly along a trench, the movement does not end at the seafloor. A sudden release of accumulated stress can lift or drop vast sections of crust by several meters in a matter of seconds. Because the ocean rests directly above this boundary, any vertical displacement of the seabed pushes against the water column, transferring energy upward through thousands of meters. Unlike surface waves shaped by wind, these disturbances originate from below. When the seafloor rises, it elevates the overlying water, creating a broad dome that begins to travel outward. If the crust drops, the water above follows, forming a corresponding depression. Gravity works to restore balance, and the displaced water spreads across the ocean basin as a series of long wavelength waves. In deep water, these waves may pass unnoticed by ships, their height modest, yet their speed exceeding that of a commercial aircraft. As they approach shallower coastal regions, their character changes. The seafloor begins to slope upward, compressing the energy into a smaller volume of water. Wave height increases while speed decreases, concentrating the force accumulated over long distances. What began as a subtle undulation in the open ocean can transform into a towering surge upon reaching land. History provides solemn examples of this process. In 2004, a powerful megathrust earthquake along the Sunda Trench off Indonesia displaced a massive portion of the seabed, generating a tsunami that crossed the Indian Ocean. Coastal communities in Indonesia, Sri Lanka, India, and even East Africa experienced devastating impacts. In 2011, a similar mechanism unfolded along the Japan Trench, where sudden uplift during the Tohoku earthquake sent waves toward the Japanese coastline, leading to widespread destruction and long-term consequences for infrastructure and energy systems. Trenches are particularly associated with such events because they mark subduction zones capable of storing immense strain. When the locked interface between plates slips, the vertical component of motion is often sufficient to disturb the overlying ocean dramatically. Not every earthquake along a trench produces a significant tsunami, yet the potential remains embedded within the geometry of the boundary. The influence of these events extends beyond immediate coastlines. Tsunamis redistribute sediments, alter coastal topography, and leave geological signatures that scientists study to understand past seismic cycles. Early warning systems now monitor seismic activity and ocean level changes, providing precious minutes of notice to vulnerable regions. Beneath the calm expanse of the open sea, the connection between trench and shoreline persists. A shift along the deep boundary can send energy across entire basins, linking distant continents through waves born in darkness. The trench, shaped by slow convergence, occasionally reminds the surface world of its presence through sudden and far-reaching motion. Despite distance, cost, and uncertainty, research vessels continue to return to the trench. The motivation does not rest on spectacle or conquest, but on a quieter impulse that has guided inquiry for centuries. Curiosity persists, even where conditions are extreme, shaped by a desire to understand how Earth functions beyond the boundaries of daily experience. Geologically, trenches represent active interfaces between surface and interior. Observations gathered from these depths refine models of subduction, earthquake cycles, and mantle circulation. Sediment cores retrieved from hadal plains preserve records of past seismic events and climatic shifts, layered in sequences that extend far beyond written history. By analyzing mineral transformations and isotopic signatures, scientists trace the pathways of crust as it descends and interacts with deeper materials. Each dataset strengthens the broader picture of planetary dynamics, connecting local measurements to global systems. Biological exploration adds another dimension. Organisms adapted to immense pressure and limited energy challenge assumptions about the boundaries of life. The study of their proteins, membranes, and metabolic strategies informs fields ranging from biotechnology to evolutionary biology. Enzymes that remain stable under compression inspire industrial applications, while genetic analyses illuminate pathways by which species adapt to isolation and scarcity. Discoveries made in the trench ripple outward into laboratories, influencing research that may never involve the ocean directly. There is also relevance beyond Earth. Conditions in the Hadal Zone resemble, in certain respects, environments suspected beneath the icy crusts of moons, such as Europa and Enceladus. By examining how life persists without sunlight, supported by chemical energy and shielded from extreme pressure, scientists gain analogs for potential extraterrestrial ecosystems. Techniques developed for deep-sea exploration inform the design of probes intended for distant worlds, linking trench research to planetary science. Curiosity itself evolves as knowledge accumulates. Early expeditions sought simply to confirm depth and survival limits. Contemporary missions aim to map microbial diversity, quantify carbon flux, and monitor tectonic motion with increasing precision. Questions become more refined and methods more sophisticated, yet the underlying drive remains consistent. The trench offers a natural laboratory where processes that shape continents and sustain unusual life forms operate in concentrated form. Returning to these depths is not an act of defiance against the ocean, but a continuation of careful observation. Each descent extends a thread of understanding into a region once thought inaccessible. In doing so, scientists acknowledge that even the most remote environments contribute to the coherence of Earth's story, and that patient exploration, guided by evidence and imagination, remains a central part of how that story is told. The descent begins with release rather than motion. Ballast is adjusted, systems checked once more, and the surface slowly recedes above the small viewing port. There is no sudden plunge, only a gradual sinking measured in meters per minute. Inside the sphere, time stretches gently as the ocean closes overhead. For a while, light lingers. The upper layers glow in softened blues, filtered and diffused by water that grows darker with each passing interval. Crew members watch the shifting shades without speaking much, aware that this fading is a one-way transition for the duration of the dive. The boundary between illuminated and unlit water drifts upward until it vanishes entirely, leaving only the reflection of instrument panels against the glass. Hours pass in steady descent. Depth numbers increment in calm succession across digital displays. The sensation is less like falling and more like suspension, as if the vessel were held in place while the ocean quietly rearranged itself around it. Occasionally, a faint sound travels through the hull, a subtle creak or metallic sigh as materials adjust to increasing pressure. These noises are anticipated, studied during testing, understood as part of the structure's response to compression. Even so, they carry a presence, reminders that the boundary between interior and exterior is both strong and finite. Within the confined space, movements are deliberate. Crew members share tasks without wasted motion, passing checklists and confirming readings. Breathing becomes a steady rhythm, blending with the soft hum of circulation, fans, and electronic systems. Conversation remains measured, not out of tension, but because focus narrows naturally in an environment where every action has been planned in advance. There is no horizon to orient the senses, no shifting clouds to mark the passage of time. Instead, awareness centers on instrumentation and the quiet companionship of those inside the sphere. The outside world has condensed into data streams and faint acoustic signals from the support vessel far above. Each update arrives with a slight delay, reinforcing the sense of vertical distance. As depth increases, the knowledge of surrounding pressure remains abstract yet constant. The hull encloses a pocket of surface conditions, while the ocean exerts its immense force beyond. Controlled calm is maintained, not through denial of risk, but through trust in engineering and preparation. The descent continues at its patient pace, and within the small sphere, human presence endures, carried downward through darkness by careful design and steady attention. Across the Pacific and beyond, deep ocean trenches trace long arcs along converging plate boundaries, each shaped by its own geological history. Though separated by thousands of kilometers, they share a common origin in subduction, where one plate bends and descends beneath another. Yet no two trenches are identical, and their differences reveal the varied character of Earth's restless crust. The Tonga Trench stretches along the boundary between the Pacific Plate and the Indo-Australian Plate. It is among the deepest and most seismically active regions on the planet, with sections descending beyond 10,800 meters. Here, plate convergence occurs at a relatively rapid rate, driving frequent earthquakes and vigorous volcanic activity along nearby island arcs. The trench walls are steep, and seismic records indicate intense deformation within the descending slab. Researchers studying Tonga often focus on how fast-moving subduction influences mantle circulation and the generation of magma. South of Tonga lies the Kermadec Trench, forming a continuation of the same tectonic system. Its depths approach similar extremes, though its seismic patterns differ subtly due to variations in plate geometry and age. The Pacific Plate here is older and colder, altering the way it bends and fractures as it sinks. Hydrothermal systems and volcanic islands punctuate the region, offering insight into the interplay between deep subduction and surface expressions of volcanism. Biological surveys have revealed distinct communities adapted to the trench's specific chemical and geological conditions. In this broader landscape of hadal environments, Galathea Deep occupies a quieter but equally significant position. Located within the Philippine Trench, it forms part of a complex network of interacting plates in the Western Pacific. Convergence rates, slab composition, and regional tectonics differ from those in Tonga and Kermadec, shaping unique patterns of seismicity and sediment distribution. While its maximum depth is slightly less than the deepest points of Tonga, it remains among the most profound depressions on Earth. Comparing these trenches highlights how depth alone does not define importance. Each site offers a distinct laboratory for understanding plate dynamics, earthquake behavior, and biological adaptation. Variations in temperature gradients, sediment supply, and chemical flux create subtle differences in habitat, influencing which organisms thrive and how geological processes unfold. Together, These hadal trenches form a global network of extreme environments linked by the common mechanism of subduction. They mark the edges of moving plates, outline the contours of continents, and contribute to the recycling of crust on a planetary scale. Galathea Deep fits within this network not as an isolated anomaly, but as one expression of a larger tectonic mosaic, its character shaped by local conditions, yet connected to a worldwide system of converging boundaries. Even after decades of sounding lines and digital surveys, vast portions of the trench remain only partially resolved. Maps display sweeping contours and depth gradients, yet between those lines lie steep escarpments and narrow gullies that have never been seen directly. Sonar passes reveal outlines, but fine-scale textures and hidden overhangs often escape detection. The slopes that descend toward the deepest axis may conceal fractured ledges and isolated basins, shaped by events that have not yet been recorded. Autonomous vehicles have traced selected corridors, producing high-resolution mosaics of sediment ripples and rock outcrops. Still, coverage is fragmentary. Large stretches await systematic exploration, their features inferred rather than observed. In regions where seismic activity has shifted the terrain, earlier data may already be outdated, leaving subtle changes undocumented. The trench evolves slowly in human terms, yet continuously in geological time, and not every transformation is captured. Biological knowledge remains similarly incomplete. Samples retrieved from sediment cores and baited landers suggest that species diversity increases with careful sampling. Genetic sequencing has revealed microbial lineages unlike those found elsewhere, hinting at evolutionary paths shaped by isolation and pressure. Larger organisms, too, may occupy niches beyond the reach of existing cameras. The hadal realm's sparse populations and vast area make comprehensive surveys challenging. A single expedition might document a handful of species, while neighboring valleys remain unvisited. Some adaptations observed in known organisms raise further questions. Variations in membrane chemistry, enzyme stability, and skeletal structure suggest evolutionary experimentation over long periods. Yet the full extent of this diversity is uncertain. Without continuous monitoring, seasonal patterns and reproductive cycles are difficult to discern. It is possible that transient communities assemble around episodic food falls or chemical seeps, appearing and dispersing without ever being recorded. Geological uncertainty adds another layer. Subduction zones involve complex interactions between descending slabs and the overlying mantle. The precise angle of descent, the rate of fluid release from minerals, and the distribution of stress along the plate interface are subjects of ongoing research. Instruments placed on the sea floor measure tremors and deformation, but coverage is sparse compared to continental networks. Small shifts in the trench floor may signal deeper processes that remain only partially understood. The trench, therefore, is not a finished chapter in scientific understanding, but an open field of inquiry. Each dataset clarifies certain aspects while revealing new gaps. Unmapped slopes, unclassified organisms, and unresolved tectonic dynamics coexist within a landscape shaped by immense forces. What is known forms a framework, yet beyond it lies a substantial margin of uncertainty, inviting continued observation and careful interpretation. Progress in deep exploration rarely arrives as a single breakthrough. It advances through refinements in materials, electronics, and algorithms that gradually extend the reach of human inquiry. Laboratories and shipyards continue to experiment with alloys and composites designed to withstand extreme compression while reducing overall weight. Advances in titanium processing, ceramic matrix composites, and novel carbon-based materials promise hulls that maintain strength with improved durability over repeated dives. Engineers also study how materials respond to cyclic stress, since each descent and ascent imposes subtle strain. By modeling microscopic fractures and fatigue patterns, they aim to design pressure spheres and structural components that endure longer operational lifetimes. Transparent ceramics and reinforced acrylics are being evaluated for viewports capable of maintaining clarity under immense load. These developments do not eliminate risk, yet they expand the margins within which exploration can proceed. Robotics continues to evolve alongside material science. Autonomous underwater vehicles are becoming more energy efficient, equipped with advanced battery chemistries and improved power management systems. Modular designs allow sensors and sampling tools to be swapped depending on mission goals, increasing flexibility without redesigning entire platforms. Thruster systems are refined to operate quietly and reliably in dense water, while manipulators gain dexterity through improved actuators and feedback controls. Miniaturization plays a crucial role. Smaller instruments can be deployed in greater numbers, forming networks across sections of the trench. Distributed sensor arrays may record seismic activity, chemical gradients, and biological movement over extended periods. Instead of relying solely on brief visits, researchers can begin to monitor hadal environments continuously, gathering time series data that reveal patterns previously unseen. Artificial intelligence is increasingly integrated into navigation and data analysis. Machine learning algorithms process sonar returns and visual imagery in real time, identifying anomalies and guiding vehicles toward areas of interest. Autonomous systems can adjust course based on terrain features, maintaining safe distances from steep walls without constant human input. AI also assists in interpreting the vast datasets generated during missions, distinguishing biological forms from geological structures and flagging subtle changes between surveys. Communication technologies are being refined to improve bandwidth and reliability in deep water. While acoustic signals remain essential, hybrid approaches combining acoustic and optical methods are under investigation. Enhanced compression techniques allow more information to be transmitted within limited channels, strengthening coordination between surface vessels and submerged craft. The future of deep exploration rests on the convergence of these innovations. Stronger materials extend endurance, refined robotics broaden reach, and intelligent systems enhance decision-making. Together, they suggest a gradual transformation from isolated descents toward sustained presence, where the deepest trenches become less sporadic destinations and more continuous fields of study, illuminated not by conquest, but by careful advancement in science and engineering. Not every frontier becomes a destination, even when technology makes arrival possible. In research planning rooms far from the ocean, decisions are shaped by balance rather than ambition alone. Each proposed expedition is weighed against competing goals, finite budgets, and the practical limits of time at sea. Risk and reward form part of that calculation. Hadal descents promise valuable data, yet they also demand complex logistics and carry inherent uncertainty. Instruments may fail, weather may shorten operations, and results are never guaranteed. When agencies distribute funding, they consider how likely a mission is to produce broadly applicable knowledge. Coastal studies, climate monitoring, and fisheries research often yield immediate societal benefits, influencing food security and environmental policy. By contrast, trench exploration may generate insights that are profound but less directly tied to daily concerns. budget priorities reflect these realities. Oceanographic institutions manage fleets, laboratories, and long-term monitoring programs. Allocating millions of dollars to a single deep descent means postponing or reducing other projects. Satellite observations, autonomous surface vehicles, and coastal sensor networks can collect data continuously at lower cost per hour. Administrators must evaluate how to maximize scientific return across diverse fields, from atmospheric science to marine ecology. Strategic research choices also depend on international collaboration and national focus. Some countries invest heavily in deep-sea technology as part of broader technological development, while others emphasize renewable energy, polar research, or space exploration. Geographic proximity influences engagement as well. Nations with direct access to certain trenches may prioritize them, whereas distant regions require extended voyages that strain logistical capacity. There is also the matter of incremental knowledge. In areas where baseline data remains scarce, initial surveys may be justified. Once fundamental parameters are established, subsequent missions might shift toward more detailed or comparative studies elsewhere. Exploration proceeds in stages, and attention moves according to emerging questions. A trench that has been sampled a handful of times may not receive continuous visits if pressing hypotheses can be tested more efficiently in other environments. The result is that some places, though accessible in theory, remain rarely visited in practice. Their depths do not diminish in significance, yet they wait between expeditions while resources flow toward other priorities. This pattern reflects not indifference, but the complex architecture of scientific planning. Within that framework, the trench stands as one of many compelling destinations, chosen carefully when objectives align with opportunity and means, and left undisturbed when other questions call more urgently for investigation. Preparation for a deep descent is neither reckless nor purely bold. It unfolds through meetings, simulations, and repeated testing, where enthusiasm is tempered by deliberate analysis. Every mission plan reflects an understanding that curiosity must be paired with restraint. The ocean does not reward improvisation at extreme depth, and so courage is expressed through careful calculation rather than dramatic gestures. Calculated risk begins with engineering assessments. Designers determine maximum operating depths based on material strength, fatigue, life, and safety margins. Pressure hulls are rated beyond their intended use, yet never without limit. Test dives incrementally approach target depths, allowing teams to observe performance and refine procedures. Sensors monitor stress, temperature, and structural response, translating physical strain into data that can be evaluated calmly on the surface. Within these parameters, crews train extensively. Emergency protocols are rehearsed until they become second nature. Redundant systems are installed so that a single failure does not escalate into a crisis. Decisions about weather windows, dive duration, and equipment deployment are guided by experience and conservative thresholds. If conditions shift beyond acceptable bounds, missions are postponed without hesitation. The willingness to delay is part of the discipline that sustains long-term exploration. Engineering limits are acknowledged rather than challenged for spectacle. Materials, no matter how advanced, possess finite tolerance. Batteries deplete, seals age, and electronics degrade with repeated exposure to pressure and cold. Recognizing these constraints allows teams to schedule maintenance and retire components before they approach failure. Innovation proceeds step by step, extending capability gradually instead of leaping beyond proven boundaries. Scientific responsibility extends beyond the safety of crew and equipment. Researchers consider environmental impact when deploying instruments or collecting samples. The Hadal ecosystem, though sparse, is not expendable. Sampling strategies aim to minimize disturbance, and debris management protocols ensure that nothing unnecessary is left behind. Data gathered from each mission are shared within the scientific community, contributing to collective understanding rather than remaining isolated. This balance between courage and caution defines the culture of deep exploration. Ambition drives the desire to reach further and learn more, yet it is anchored by methodical planning and respect for physical laws. Success is measured not only by depth achieved, but by the reliability of results and the preservation of both human life and fragile environments. In the quiet space between bold intention and measured restraint, exploration continues. It advances through disciplined effort, where risk is acknowledged, limits are studied, and responsibility guides action as steadily as any compass. There is a quiet recognition that comes with descending beyond the reach of sunlight. It is not dramatic or sudden, but gradual, like the fading of familiar reference points. Humans evolved on land and along coasts, shaped by air, gravity, and open horizons. Our senses are tuned to light, our lungs to breathable atmosphere, our bodies to modest pressure. In the Hadal depths, these assumptions no longer apply. Galathea Deep, like other trenches, underscores this reality with clarity. Survival there depends entirely on technology, on carefully engineered spheres that recreate surface conditions within a small enclosure. Outside that boundary, the ocean remains indifferent to human presence. Pressure, temperature, and darkness persist according to physical laws that cannot be negotiated. The trench does not resist exploration, yet it does not accommodate it either. This contrast reveals the extent of our dependence on tools. Every descent relies on materials forged through industrial processes, on navigation systems calibrated through satellite networks, on communication methods that translate sound into data. Remove these layers of support, and human life cannot endure at such depth. The ocean sets boundaries not out of hostility, but through the simple fact of its density and scale. Not every frontier yields easily, and the Hadal Zone offers a measured reminder of that truth. Unlike mountain peaks or polar regions, where the body can adapt with training and equipment, extreme ocean depths require complete environmental separation. There is no gradual acclimatization to 1,000 atmospheres of pressure. Instead, there is only the interface between fragile interior space and immense exterior force. Yet within these limits lies insight. Recognizing boundaries clarifies the scope of human capability. It highlights the ingenuity required to extend observation into hostile environments and the patience needed to gather knowledge incrementally. Each mission represents an agreement with reality, acknowledging that certain conditions cannot be altered, only navigated. Galathea Deep therefore reveals both constraint and possibility. It shows that humans remain surface creatures, shaped by evolutionary history, yet capable of designing instruments that briefly bridge the gap between habitats. The trench stands as a vast reminder of scale, where water columns dwarf individual effort and geological cycles outlast civilizations. In confronting such depth, there is no conquest, only encounter. The ocean establishes the terms, and exploration proceeds within them. Through this exchange, the limits of our biology become clear, as does the reach of our curiosity, extending carefully into regions that will never become home, yet still invite understanding. Beneath the shifting surface of the Pacific, far below storms and shipping lanes, the trench rests without spectacle. There are no hidden kingdoms waiting in the dark, no colossal shapes circling beyond the reach of light. The imagination often fills deep water with creatures born from fear or folklore, yet the Hadal world is governed by simpler forces. Gravity draws water downward, layer upon layer, until its mass presses against the seafloor with steady persistence. That pressure does not surge or roar. It exists as a constant, a quiet equation expressed in depth and density. Molecules compress against one another, transmitting force evenly in all directions. The result is not dramatic, but absolute. Steel must curve inward to withstand it. Electronics must be sealed from it. Organic tissue must adapt or perish within it. Geology shapes the trench more decisively than legend ever could. Tectonic plates converge, one sliding beneath the other in a slow descent measured in centimeters per year. Over millions of years, this motion carves a depression of extraordinary scale. Sediment settles along its slopes, carried from distant rivers and coastal shelves, accumulating in layers that record ancient climates and shifting currents. Occasional tremors ripple through the region, adjusting angles and redistributing material with mechanical precision. The water itself is not empty. Particles drift downward from productive surface waters, fragments of once living organisms that become nourishment for life adapted to scarcity. Microbes process chemical compounds within the sediment, drawing energy from reactions that unfold without sunlight. Fish and invertebrates move with unhurried efficiency, shaped by evolution to conserve energy in an environment where resources arrive unpredictably. Their forms are not monstrous, but specialized, refined by constraints rather than extravagance. Sound travels differently at such depth, bending through gradients of temperature and salinity, yet it obeys acoustic laws. Light does not penetrate, not because darkness possesses intention, but because photons are absorbed and scattered long before they can reach the bottom. Temperature hovers near freezing due to the circulation of deep ocean currents, not due to any hidden chill beyond explanation. The quiet reality beneath us is therefore composed of measurable forces. Physics dictates compression and buoyancy. Chemistry governs metabolic pathways. Geology sculpts contours over vast spans of time. The weight of water, extending for kilometers above the trench floor, is both the defining characteristic and the simplest fact. In acknowledging this, the Hadal zone becomes less a stage for fantasy and more a testament to consistency. It reflects the same natural principles that operate at the surface, expressed under extreme conditions. There are no myths required to explain it, only patience, observation, and an acceptance that the deepest parts of Earth are shaped by the same laws that hold the sky in place and keep continents in motion. At the end of every mission, ascent replaces descent, instruments are secured, ballast is released, and the long return toward lighter water begins. Yet the trench itself does not rise. It remains where tectonic forces have placed it, anchored in the slow convergence of plates that continue their motion regardless of observation. Far below familiar currents, its walls trace the boundary between immense slabs of crust. Along that boundary, strain accumulates over decades and centuries, then releases in sudden adjustments that ripple outward through the planet. These movements influence the pattern of earthquakes across entire regions. They alter the contour of the seafloor, shift sediment, and on rare occasions displace water in ways that reach distant shores. The trench participates in these processes quietly, as part of a global system that recycles oceanic crust and reshapes the architecture of basins. Within its depths, Life persists according to rules refined under pressure and scarcity. Cells operate without internal air spaces, membranes remain flexible despite compression, and metabolic rates adjust to limited energy supply. Organisms feed on what drifts downward or on chemical gradients within the sediment. They move slowly, conserving resources, occupying niches that exist only in darkness. Their presence affirms that adaptation can extend into conditions once considered prohibitive, though always within biological limits. Human visits remain intermittent. A research vessel may hover above for weeks, deploying vehicles and recording data, then depart as schedules and weather dictate. Months or years can pass before another expedition returns. During those intervals, the trench continues unchanged by absence. Currents circulate, sediments settle, plates advance by imperceptible increments. No marker on the seafloor records human curiosity. Only instruments left intentionally remain as silent observers. The trench rests beyond routine human reach, not because it resists, but because access requires sustained effort and resources. Each descent represents coordination across disciplines, from engineering to geology to biology. Such coordination cannot occur constantly. It emerges when objectives align and means allow. In this rhythm of approach and withdrawal, a balance forms. The ocean's deepest contours remain largely undisturbed, shaping earthquakes and influencing ocean chemistry as they have for millions of years. Human understanding expands gradually, informed by careful study rather than continuous presence. As surface light shimmers above distant waves, the hadal floor lies in enduring stillness. It is part of Earth's ongoing story, steady in its role, holding extreme life and tectonic power within a vast column of water. For now, it remains a place visited with intention and respect, then left to its own enduring processes.